Okay, welcome everyone again. So this is a continuation of the last semester's course. It's good to have, for if we follow the previous one, but for many parts of it, it won't be strictly necessary. And actually today I will recall everything, so probably it's not even necessary that you were here before. Okay, let me call it Generalized Geometry 2. The idea is to do kind of some more advanced and not technically more advanced, but maybe it's not like more sort of, let's call them more advanced aspects and some applications in the context of string theory and supergravity and maybe Ricci flow. Let's see. So literature, so you can check the online description of the course. So as before, I think a good thing might be the book by Streets and Garcia Fernandez. You can find it online. Good. Okay, so now what is the book called? Is Generalized Ricci flow? Generalized Ricci flow. In this instance, spelled with a Z.
Yes, the bird way.
Streets and the other way around. Alphabet Garcia Fernandez and Streets. Yes. And also Marco Gualtieri's thesis is also a general good source. This is just okay. Those are some good materials. So now the contents of this term, semester. So we will start with a brief recollection today, but then we will start with what I would call generalized Riemannian geometry. So in some sense, you can view what we've done the past semester as some sort of, at least in the Courant algebra part, as some sort of like a bare structure, like some sort of like replacement for a manifold in some sense that will make precise. And in this case, we're just equipping it with more structure. In this case, some sort of analog of Riemannian metric. And we might discuss how this is related to strings. Actually, today I will probably split that. String theory and maybe supergravity. Oh, maybe that's it. Okay. And the second part, we will start with Courant algebra. Some new operations, so Courant algebra reductions. And also something that I will call pullbacks. Some sort of ways to produce new Courant algebras out of old ones. And we will see how this is related to dualities in string theory. So this is related to what is called T-duality, or more generally, Watson-Lee T-duality. So these are the two main parts. And then if time permits, then there might be a last part where I can talk about more like supergravity stuff, like the super part of supergravity. I will talk about spinors, Dirac operators, of some form of kind, and supergravity, if the time permits. And okay. Now let me start by sketching. Let me start by sort of motivation for the first part, and or maybe if there are any questions, then let me know. Let me start with generalized Riemannian geometry. And more precisely with motivation. Okay, so this will be, as usual, for motivation, this will be slightly more hand-wavy, which gives me a little bit more freedom, and maybe to share some sort of more ideas about where this comes from. And okay, so I was thinking about how to start, and I think I find the following thing maybe good. So let me talk first about the theory of a charged massless particle. Okay, so this is some words. Particle, let's say. Or more precisely about the geometry of such thing. So what does this mean? So to explain the word, so what I mean by theory in this context, I mean a variational problem. And what do I mean by charged massless particle? I mean the following picture. So imagine that you have a smooth manifold, M. You should think of this as space-time. E.g. R to the D times R. So there's like one specific, you can think about it like in some favorable cases you have like one preferred direction which you call the time. And if you have a particle that moves in such a thing, then for every time element it will correspond to a point in here. So adding this thing would make it a curve. Now doing that more generally, a particle would be something that corresponds to some sort of curve. So there's a curve. Now I used my opportunity to use color, okay? Imagine that this is red. Yeah, this is space-time. Now I'm going to use a color. That's what you should think about. So the space-time usually comes equipped with more structure. In this case, I will equip it with a metric. Ideally, this metric should be Lorentzian, so it should have some specific non-positive definite signature, but the signature for us is irrelevant. So just think about this as a symmetric non-degenerate two tensor. So, yeah. Think about it, you can take a positive definite if you want. And now when I say variational problem, what I mean is that we are interested now in looking at such curves. So more properly, I should say that gamma is a map from an interval. 0 to 1 to m, and I am defining a action function, so function on the space of such curves. I take things to be the length of gamma. Length measured with respect to the underlying Riemannian metric. Okay. Properly, if you want, I pull back the metric to this along gamma to the interval, where it becomes a metric of an interval, and then I integrate the lines of that. Okay? So this is a famous variational problem. You know that by looking for the external of this, you end up with geodesics and this Riemannian manifold or manifold with metric. So this is an interesting question. You know, like what is this? So this thing would kind of correspond to the theory of a massless particle. So, but in some way, that I'm not because okay, we didn't write any mass anywhere, so this is a massless particle. You know that if you throw some particle in a space with a metric, then that one is supposed to follow the geodesics. So that's got, you recover it as the external of this function. Now, when I added the word charged, this means that there is a more geometric structure here. So there is something that the experts might call a electromagnetic field. For us, it will be a one form on M. So this is the data that we have. And it enters in here, right? So this length, it used the first piece of data, it used the metric. But now I can do a second thing in a very natural way. I can use this one form, and I can integrate it over the curve. Okay? Because here it's important that the curve is a one-dimensional object, and I'm integrating a one form over that thing. So now we get a new variational problem, and again, it's true that so this is describing some charged massless particle moving in some background with some electromagnetic field and metric. And the physical trajectories that such particles will cut out correspond to external of this. Okay. That's what I wanted to say at this stage. Now, maybe one remark, because this is a kind of a geometric class. So, you might know that the more proper interpretation, more proper or geometric picture, so instead of talking about one form, we actually have a principle U1 bundle with connection. This A, in fact, is not a one form, but it's a connection on a principal envelope. And the above picture context corresponds to the case when this bundle is trivial. Yeah, any questions?
So where does gamma is in this case curve in what?
Gamma is a curve in the base of that. So 1 over m. And gamma is still a curve in m. But now this last term, or more properly the exponent of the last term, is replaced by holonomy, by the holonomy along the curve.
So you didn't have the exponential before, so...
No, I didn't. Yeah, I think for holonomy you want it to be group valid, so it should be non-exponential. So properly, yeah. So this is, as you see, if you're familiar with whatever quantum stuff, then usually have exponentials of actions. So the more proper geometric interpretation is actually that you have a Riemann manifold U1, and then you have a U1 bundle with connection over that. And then, well, actually, this thing is it's this thing. So it's replaced by holonomy. Okay, but we won't be sticking to the first big point. It's just to say that there is some interesting geometry happening.
But then if you want to write with the actions, you would take quite well this, or would you do too?
Well, you wouldn't. I mean, in this case, this thing by itself is only well defined up to z.
But then if you want to consider a variational principle, you don't vary the exponentiated action, but the action itself. So
yeah, but you don't consider a variational problem if you do the quantization.
Okay.
Yeah, so these are good questions. I didn't want to touch them. Yes, I guess you can say that, right? Or I mean, even.
I mean, this thing you insert in the path integral, probably. Then that's it.
Yes. But actually, for a variational thing, it probably doesn't matter if it's valued in z. Sorry, in r on z. It's okay. Variational problem. Maybe. Anyway, it's just to say that you study questions, electromagnetism, and all that stuff. Then this is. But I mean, this term is the interaction of the electromagnetic field with the particle. Like, how does the particle feel the electromagnetic field? Properly, that should be multiplied by the charge of the particle. So there's some coefficient there. So, okay, that's all I want to say for a particle. Any question? Let's do the more exciting part, which is now what happens if we go one dimension higher. So this is theory of, I call the theory of charge mass quality of particles, so this will be theory of strain. Now the picture of the draw. Okay, we'll go there. So you have a manifold. Already you can already expect that there will be some sort of metric there. But instead of a trajectory, if you have a string, by string you imagine some sort of circle, like at every spatial slice, for every constant. If you imagine it in this simplified setting, at every given time, so which means that every constant, I take this coordinate constant, there will be some sort of loop in here, or maybe an interval, depending on what kind of flavor of string you're interested in. And now, in the whole thing, it will cut out the surface. So at every point, it's a one-dimensional thing. Overall, it will be some sort of surface. The picture to have in mind, I can imagine that it's something like this. add some genus. And again, I want to consider this a variational. That's a variational problem. So again, I want to write down some sort of. Let's do this. Okay, so again, to be more formal, what we want is really if you have some sort of map. So interval is replaced now by sigma, which is a two-dimensional manifold. And it gets mapped into M. You can ask which two-dimensional manifold. I mean, there was an interval, which is kind of the only thing that you can do apart from circle. Now there is a plethora of this. So which one? So let me ignore that. I'll just choose one for now. And then we can write down a variational problem which will depend on x, strictly speaking, okay? Which will be the area. Now that's the natural area of sigma. Okay, let me use the notation. I mean, area. I really mean area of of x. I use x to call it back, but I mean in the picture clearly this is simply the area with respect to the underlying metric. So this thing in string theory, this thing is called an Ambugoto action. And in some sense, you can regard it as a starting point for string theory. But now I want to. The reason I was drawing it in this succession is that now there is a sort of natural form that you can put in there. So just as before, you can try to add another term where. Well, what should you integrate now?
5.
Any other solution? 2 form. Good. And the natural name for that is indeed B. It's like A is, first letter of alphabet, this is second. I think that's probably the all nomenclature reasoning that there is to it. So, okay, so what we have here is indeed that there's like a natural replacement of the previous setup is that there is a 2 form. And indeed, this is kind of if you want, like, I don't know, enhanced string action or something like this is a natural action for string theory. Even maybe some people would even maybe call the whole thing but okay, it doesn't really matter. But okay, so yeah, you should again regard it as a string moves in space-time and it feels the metric, and it also feels the 2 form, so it's charged with respect to this 2 form thing. So more precisely, again, let's write this a remark. More precisely, or more properly, instead of talking about sorts, we want to again talk about connections of some sort. So in this case, and principal bundles. So in this case, more properly, we have what is called a U1 with connection. Connection on B. So this B is a connection in some higher sense. And a higher replacement for a principal bundle is something that's called the Gerb. And again, this term, exponentiate, is replaced by in some appropriate sense. Sigma. But I'm not going to go into this. This is just to say there's some interesting sort of higher geometry hiding behind this, where connections are not 1 form, but 2 forms, 3 forms, etc. But for us it will be sufficient, most probably, to just stick to this setting, at least for now. Okay, so let me now very optimistically say that this is the start of what we said. So this is kind of the starting point for string theory. Was this persuasive to some extent? That this is a natural thing to do? It's not clear why it should be 2-dimensional, why not like 7 or something. Yes. So let me not address that, maybe for now. But let me say another thing. So there is this sort of black box. Let's say, so far the thing I described was a classical problem. So you have some geometric data, you have some maps, you have some function of these maps, and you're trying to extremize it to find out the trajectories. But what you ultimately want to do is to quantize the thing. And in quantization, roughly speaking, what you are doing is that you are examining not just the extrema of this functional, but you are integrating in some sense over the space of all such maps, in some sense. And well, there is some standard ways how one does quantization, and it turns out that for one reason or the other, it turns out that in order for this theory to be correctly quantizable, in order for this to quantize, okay, this is the black box part of it, I will only do the second part of the sentence, quantize nicely, properly, whatever. This data needs to be subject to some constraints. In concrete, there needs to be a fixed point of what is called a renormalization group flow. Okay, let me not explain in more detail why it is necessary, let me just tell you what the flow is. So what does this mean? So instead of considering the data that I just gave you, let's suppose that we have a family. G and B depending on some auxiliary parameter lambda. And then we formulate a common differential equation. You add those two things together. They are, after all, covariant two tensors. They are both elements of the T star and the T star at every point. And I will and this. So you know from Riemannian geometry probably that if you have a metric, then it is a symmetric two tensor. Now, for a metric, with metric you can do many tricks. One of them is that you can calculate its curvature. In particular, you can get the Ricci tensor, which is again a symmetric tensor. So, like a simpler version of this thing is this. This is kind of the original thing. This is called the Ricci flow, which you might have heard about. It's a differential equation where you have a family of metrics such that you deform the metric as you go along lambda by adding a little bit of the Ricci tensor to that. So it's a very interesting question of like to study. I mean, this is a very interesting problem and very useful kind of gadget to have and study. And as you might know, this led to some solutions of famous problems in geometry. This is kind of a sort of natural analog of this, because this object here, this thing is the Ricci tensor. To define it, this is the Ricci tensor for the metric connection with torsion. Torsion given by B. Torsion is dB. Okay, so if you know about Riemannian geometry, you know that for a metric, you can construct metric, you can study metric connections with vanishing torsion, and using them you can construct Ricci tensor, which is this thing here. But now, in the presence of this B thing, this becomes modified. You still can construct the Ricci tensor for that. It will no longer be symmetric; it will have an antisymmetric part, which is what you are using as effectively to deform this antisymmetric part of this expression. This is symmetric. This is antisymmetric. Okay, does that make sense? So there is some sort of equation. And strictly speaking, I didn't really need the equation. I do that just because I'm anyway saying that it needs to be a fixed point of this flow, which means that essentially this thing right hand side is 0. So I could have just as well said that Ricci is 0. That's the condition for this background to be quantizable nicely. But instead I'm saying, but there is a whole thing behind, it's called the renormalization group flow. It corresponds to that. Okay, I don't know. Okay, I don't know where I was going with this, but let's consider the whole flow, not just the fixed points, because it's an interesting kind of question. Maybe there is plus minus. I don't remember.
Does Dilatov enter?
Yes, soon, very soon.
But is it natural from the point of view of generalized Riemannian?
Yes. So yes, for those of you who know about string theory, then string theory famously, well, string theory describes many fields, and this metric and this thing which is incidentally called B field. It's easy to remember name. So that thing, those are kind of two of the protagonists, but there is another one, like the next most famous thing is a thing called the dilaton, which is a function on M. And that one also enters the story soon. Actually, in the next sentence, I think. Okay, please ask me any questions. I know that this thing doesn't have definitions yet, because we will do more definitions in a bit.
So this is, I guess, the equation for leading order in alpha prime in string theory, right?
Yes.
Is there a geometrical nice, generalization for any truncation to any order of alpha prime, or is this really like very special?
You mean in terms of general geometry?
Yeah.
Okay, okay, many people are studying this question. I don't have anything to say beyond the leading order in alpha prime or G string. I would probably I don't really know. I mean, I personally don't really see any reason why this description should be applicable to the description that I'm going to give you, why that should work for higher order terms. But then again, there is an interpretation of the sigma model from the world you think in terms of generalized geometry. So if you see the whole string theory originating from there, then there should be some sort of artifact on that side as well. But I can't say anything concrete about that. But good question. Okay, so now let me make the following observation. So, and this is actually something that if you open Perelman's paper on the Ricci flow, this is one of the first things that he observes or notes. That is the following thing, that this thing, actually, you can see this as a gradient flow of something. Okay, so the picture to have in mind is that we have there is some very, very big space. So this is space of all metrics, maybe plus B fields if you want, like depending on whether you do this or the more general case. We have let's do that. This is for B fields. So there is some infinite dimensional space, and there is some sort of vector field on that space. Right? That's what this thing is. It tells you how to deform a A2 by adding something to it. Okay? So although it's infinite dimensional, you can imagine there is some sort of vector field. This is Ricci. Now it turns out that on this space there is also a sort of natural metric, infinite dimensional one, but okay, whatever. And this thing actually turns out to be a gradient. This vector field turns out to be a gradient of a natural function. Okay, that's it, if you can say that. But this only works if you modify your program a little bit and introduce a new field. So this becomes a gradient flow or gradient vector field if we introduce a new variable field. I will call it phi, and it will be for now a function on the base manifold. Okay, so now maybe just illustrate what the problem is. So this is some sort of infinite dimension. Let's forget about the big field, you know, like let's do space of metrics. But can you imagine a function, you know, I'm saying that you want to have, okay, in order for this to be a gradient of a function, you need to, you know, come up with a function. Is there a natural function that you can define on the space of all possible metrics? Like a natural sort of geometric, you know, function. Is there a way to produce a number if I give you a metric on the manifold? Maybe let's use some compactness. Oh yeah, you can do volume. Okay, yes. But let's take, okay, volume famously is, okay, good, you got me there, yeah. So volume is like an algebraic thing, okay, it doesn't include any derivatives, so it doesn't lead to, it doesn't, okay, the answer that I'm looking for is not volume. Volume is too simple to make this work. There's something slightly more elaborate, but not far from that, I guess.
You can even at every point the Hilbert-Einstein action, for example, no?
Yes. So the thing I'm going for is that there is this, the natural quantity is what's called the Einstein-Hilbert action. Which is the following thing. So you take, you know, you give me a metric, and while I do the metric, I construct the scalar curvature, which is a function on the base of the manifold, and then I integrate it against the Riemannian volume. This gives me a number. And famously, what are the critical points of this? If you know, it's precisely Ricci flat things. Like the critical points of this are precisely metrics that are Ricci flat. Which sounds like, okay, that's great, that's probably the thing we're looking for, because the critical points of this are also Ricci flat. But it turns out that no, because the vector field is different. The critical points are the same, but you know that, you know, if you vary this, then you don't get, you get the Einstein tensor, not the Ricci tensor directly, but the vanishing of Einstein tensor is the same as the vanishing of the Ricci tensor. So critical points are the same, but the vector field is different. So the vector field gradient of this is actually not that thing.
So why did you consider Ricci fold and not Einstein fold?
I think that one is badly behaved from some PV point. I guess. Yeah, I think so. Yeah. So this thing. Okay. Since this was already started. So the good thing, the great thing of this thing, of why this thing is even studied, is that, well, first of all, this is a horribly nonlinear equation. Like this calculated curvature, if you know, like you first need to figure out the Christoffel symbols, and then you need to do some invert. You know, like there is. It's not even a polynomial. It's like horrible, and it has their second derivatives of the metric entering in there. But it turns out that if you pick your favorite metric and linearize Ricci tensor around it, that the leading order. If you pick a Ricci flat background, Ricci flat metric, and you express this in a neighborhood of that, so you linearize it in terms of metrics, and the leading form looks like Laplace on G. Maybe minus 1/2. On the right hand side looks like Laplace of G plus some like high order stuff, which looks like this looks like the heat flow equation. And heat flow equation is famously very nice because it leads to things like it smoothens things out. You start with some horrible stuff, and you let it flow with the heat flow, and it kind of nicely averages over. So, for instance, it turns out that if you study this thing on a Riemann surface, or like pick your two-dimensional manifold, like imagine a two-dimensional manifold, and pick any random Riemannian metric on it, any random horrible complicated one. It turns out that if you study this equation where you start with that metric and you let it flow with Ricci tensor, it will lead out the what is it called like this? It will lead to the metric with constant scalar curvature. Like it will smoothen out it will make it more round. And kind of the proposal of Thurston proposal of Hamilton, and then finished by Perelman's work, was that this is actually a great problem that you can study to tackle some big conjecture in geometry. But unfortunately, it turns out that if you go to more than 2 dimensions, then this flow develops singularities. Because I mean, this is all fine as long as you can neglect the rest, but the rest can blow up, and it does typically. So there is some singularities forming, and the story is more complicated. But the idea of why I started this one is that the linear equation that is the plus. So I think if you take the right sentence, then it won't be this. Because there is, why would it? Yeah, probably not. So yeah, that's why. Okay, so this doesn't work. But it turns out that it works if you modify your stuff and you, instead of essentially, I think the idea is that you take this thing as your separate variable. So instead of having this as you put like a theory where you would have not just a metric but also a volume form, and then the critical points of that would give you a Ricci flow. Because I think varying your scalar curvature you get Ricci directly, right? I think the fact that you get Einstein tensor is because you vary the volume. Is that right? If I remember correctly?
I think so. This version of Ricci is a total derivative, something that gives you the total derivative term.
Oh yeah, well, there's that one. Okay. Okay.
And the PDEs come from a variation of the one, if I remember correctly.
Okay.
You will not get the Ricci, no? Like the Ricci comes from somewhere.
No, I saw the Ricci type.
And if you just vary volume form, it doesn't give you Ricci, no? So then you have just a scalar curvature.
No, it gives you the del G, right? And then in front of it there is Ricci, which is just equations.
So
I think varying this you get. Okay, I will. Okay, I really should check what I'm saying. But anyway, the resolution to this problem kind of lies in taking this thing as a separate variable. So, in volume forms, in terms of degrees of freedom, is the same as functions. Just the line model. So that's why I'm talking about functions. We will get to all of that later. For now, let me just maybe write what is the proper gradient, or like the function whose gradient is that thing. I will call it S tilde to distinguish it from the other one. Okay. Okay, so there is some sort of enhancement of the story where you take. First of all, there is the B field included, because the picture, that thing, I was setting that to 0, but in print that thing is round. There's also a kinetic term for this dilaton, this thing is called the dilaton. Roughly because, I guess because, okay. I mean, you see that here it multiplies the volume form, that's the thing. Anyway, for now, feel free to ignore this. So, essentially what I'm saying is that the volume form, or rather the thing that this whole thing is something that replaces this thing, and that thing you want to take it as a separate variable, either phi or the whole thing. So you kind of resolve this thing by adding a new variable, and then it suddenly becomes a gradient form in some sort of nice way.
So all the coefficients that are they determined? Like some of them you can discuss, but is there any meaning? Is there any special choice that makes things better? Or like when you put 2 phi and all this? Like how unique is this choice?
So you can already find phi. I guess you can, when you replace phi by 1/2 of phi, and then this 4 and 2 gets absorbed. There is some conventional reasons why there is like.
But for example, the relative coefficient you cannot change, no? Like,
Well, I mean, if you replace phi by 1/2 of phi, then you can kill these two things.
yes, but if different number there, for example, you get something that is different, or like.
I mean, if I would just change this to phi.
Yeah, for example. Or 7.
Yes. So. Okay. At this stage, it's not clear why I added this term. Okay, so the relative factor here is important to get the Ricci tensor here for that thing. For the dilaton in principle here. The equation, you have a new field, so there will be also an equation which minimizes the other guy. You want that guy to be kind of the scalar curvature plus minus some other stuff maybe. So I think that might not work if you would just put a random thing in there.
But is there some kind of symmetry or some, something additional that tells you that this is the right, some higher? Yeah.
Or you mean like supersymmetry?
Yeah,
I
something.
mean, supersymmetry would be one way to.
Yeah,
Count
maybe one way, or something like something. It was a make symmetry, which
So supersymmetry definitely fixes this coefficient. That I know for sure that is true. Without supersymmetry, I mean, you can. But you can really find there is a sort of like a fielder definition that you can do, and you can move metric to like some coefficients times phi of the metric. In principle, you can do that. So you can, for instance, do this to get rid of this thing and absorb it in here. So what people call the Einstein frame, while this thing is called the string frame. So this messes up the coefficients a little bit. Modulo that I don't think so. I mean, I don't remember, but I mean, certainly you need this in order to work. I don't remember what goes wrong if you don't do that. I guess the equation for motion for real on this is not correct. I mean, also, this thing will be kind of. Okay, at this stage, I don't think we have the means to answer this question.
And if you do this thing that you wrote, with arbitrary alpha, does it stay on the same form, just changing the coefficients, or is there also other things?
I don't remember. Maybe you get some. No, maybe not. I don't remember. Maybe you create some Laplace terms on phi or something. Maybe not. I don't remember. Sorry. I don't remember. I always work with this form, so I don't care about the rest. Okay, let's blame it on supersymmetry. This thing. Okay, so this action, I will call it the string loader effective action. Or the bosonic part of supergravity. The meaning of the second meaning of this parenthesis I will get to that later on, maybe. But so far to end this kind of hand-wavy part, I want to tell you most hand-wavy thing about that's like why do I call it this? Why is this thing called string loader effective action? So before that, let me just notice the thing that the way we constructed this. I mean, I didn't prove that gradient, but if you believe me that this gradient of this is that thing, so then you'll see that the critical points of S correspond precisely to this, to the fixed point of the flow. Okay, that's the consequence of what was said about the critical points of the action is precisely the points where the gradient vanishes.
Of this S tilde?
Oh, S tilde. Yes. Okay. So now let me explain why do I call this.
What is what? This is just a classical rigid tensor, right?
This is the rigid tensor for metric connection with origin.
Okay, so it's not the generalized one.
Well, not yet, but it will be.
Huh?
I mean, so far we don't know what the generalized rigid tensor is.
Okay.
This is just ordinary geometry. The generalized geometry is only a tensor.
But you didn't tell us what is the G of G and B, no? So
Sorry?
you didn't tell us what is the G of G and B, no? So
No, I tell you, it's the rigid tensor for the unique
okay.
metric connection stored is
Okay.
given by dv.
so
This is a calculation I think goes to 7 maybe.
So you take the Chivita connection and then you add to it this BB absorption and then
Yes.
you calculate.
Does he calculate ratio that? Yes. So this goes back to the paper of Riemann, I think, in the 70s, 80s, something. For people who did some hardcore calculation of like the arbitrary this thing, and they came up with that equation.
And is there any complication when you want to calculate from the Riemann tensor the Ricci in the case that it's not torsion free, maybe it doesn't have all the symmetry properties, so is there, do you have to be careful in which indices you construct? Or?
Good question, I don't remember.
Because definitely part of the symmetry, no, of the curvature.
It depends on the
Yeah.
Yes. Yeah, I don't remember. Yeah, that's a good point. But we will soon forget these issues anyway because we enter generalized geometry where this stuff becomes kind of more. Remember that the upshot for now was that we have this. We're studying this geometry data, and maybe this delta as well. And one of the things that we are aiming for to do either today or early next time is that one of the first steps that we will do is that we will kind of replace this thing by current algebra. We will see that these two objects nicely combine into what is called generalized metric. At this stage, it doesn't look as impressive as it actually is, because I'm just saying that we can rename these two things as like one thing and do something with it. But believe me, you will see later on, this is actually quite a drastic simplification of the treatment if you use generalized geometry. So, okay, so now the head report.
So what does it mean it becomes a gradient flow?
Yeah, that was a picture I drew
Oh, sorry.
just before it came. I think that you have like,
I'm sorry if you don't, I never watched it on the video.
so you have a space of all metrics, infinite dimensional space, where every point represents a metric on the whole manifold. And the Ricci flow equation in the Ricci, you can see that the fact that you had this equation, that some derivative of g was minus 2 times the Ricci, you can see this as, it's like an evolution equation on some vector field in here. So vector field being the Ricci flow, the Ricci tensor. Because it's something that deforms your metric, so it's a vector flow in this space. And now there is a coin inverse of, there is a natural metric on this infinite dimensional space, and then there is a natural action functional whose gradient is this vector field. Okay, that's what I mean, that's a gradient flow.
Okay.
The Ricci is a gradient vector field. Okay, so now the last part, which I struggled a bit yesterday, but let's see here. Let's see. So, okay, so this requires some notions on string theory or some sort of insight. So, okay, so first, what is a string theory? So, for the purpose of what I'm saying, string theory is a very interesting and intricate machinery. Interesting, good machinery. No, I prepared the best words yesterday, so I need to.
You prepare the definition of string theory.
Yes. Yeah, and this is a full stop here. It's very interesting intricate machinery, or physical theory, which describes the quantum theory of some number of particle fields. Quantum theory of, I'll put it in parentheses, you can also do classical, but quantum. The quantum theory of infinitely many types of particles, fields. That's usually how they are described in this context. So what are those? So they correspond precisely to these guys that we've seen before, and there is infinitely many others. So the thing that I wrote here is a field in a sense that it's like a tensor field on the manifold, but the same held for the one form that we've seen before, like the electromagnetic field. And you probably know that there is this, even if you like the electromagnetic field, if you do the quantum theory of that, it describes photons. Like there's like a bunch of particles. So it's similar. There is particles behind these things. There is something called gravitons. Do people used to call this axions actually, or?
Maybe for the individualized.
Oh, okay, maybe. So some sort of generalized axions, some sort of scalar particles, and other stuff. So just think about it. There's some geometric quantities corresponding to them, which are those fields. And the string theory tells you how these things work, how to calculate scattering amplitude and all that. Now these dots that I wrote here, you're supposed to think of those as massive fields, very massive. So they correspond to fields which are very massive, very heavy, so we don't produce them in colliders unless you go to like energies close to the Planck scale. So these are very massive fields, and hence not directly appearing in our considerations. Appearing at low energies. Well, when you okay, So when talking about low energies, this is like stringy meaning of low energies, which means like the energies in the in the colliders are still like way lower than low energies of string theory. So these things you really don't see them like sorry, these ones. Okay. Apologies if it's getting a bit light for you, but anyway, there's no way around it, I believe. So now, to be more precise, so in the classical approximation, so if you forget about quantum for a moment, classical and low energy approximation. Okay, these particles, they are described again as a variational problem. That's how we do classical physics. Described by an action functional from S and string maybe. So this will be some variational problem which will involve these fields, and because I use low energy, I only care about these ones. Okay. So there is some sort of thing that comes from string theory. There is an action functional, possibly very unrelated to that one, although let me hide the previous one. So they are described by string theory produces to you this thing. That's bullet number one. The second bullet says that now if you want to do quantum stuff, so the quantum theory describes, as quantum theory too, describes fluctuations around a given configuration. And given configuration means just pick one of those things, fix them. What quantum theory does is that you have like flat space-time, for instance. That would be an example of such a data. And then you try to scatter some two gravitons. Send them from a collider, try to scatter them and see what you get. But scattering two gravitons means that you really put like some very minor fluctuation of the gravitational field when you're studying that. So fluctuations correspond to so quantum theory describes this. You should think of it as describing some sort of fluctuations around the background. And the way it does is achieve this is describes what is another. Describing, thank you. Quantum theory describing fluctuations is described again, okay, sorry. Is described using surfaces. So this is why we call it string theory. Use surfaces, aka string worldsheets. And the way you do that is that you start with that picture we had before. So you calculate this, that kind of what was it? It was like area of sigma plus maybe integral sigma of b. And the way you do stuff in string theory is that you exponentiate this, with some I, and then integrate this thing over all possible embeddings. And then you sum over all surfaces. Okay, so I'm particularly proud of this summation. Okay, and this thing gives you some sort of, but of course this is infinite dimensional, and as it stands, it's kind of meaningless. But it's kind of the art of string theory or string theorists. There's procedures how to make this expression meaningful, and it produces a bunch of numbers which are the ones that describe these quantum fluctuations. Okay, this is the reason why called string theory, because in describing this quantum theory or fluctuations around the background, we use this approach where we involve surfaces.
To me, strings are one-dimensional.
Yeah, but
Why are
this
they
is-
using two?
so two-dimensional is the you know, like a time direction. It's
Okay.
space-time is the meaningful object in
Yeah.
space.
Yes.
You need to describe the entire histories of string movements.
Okay.
Typically, there's some cylinder. If the string stand, it's a cylinder.
Okay.
Yeah, it's just that. Same with particle, you imagine as a trajectory. Yeah, that's. Sorry. So the manifolds are really not not Riemann, they're Lorentzian, they describe space, times. There's time. Does that answer your question?
Yes.
Okay, good. Okay, now the last bullet point says that, again, the black box, so for this description to be meaningful, this quantum description, or this quantum description to be meaningful, one needs to actually work not at any such thing, but it needs to be an extreme of this. One needs configuration V0, V0, Y0 to extremize S string. Because this is another important piece of knowledge in physics, that if you study excitations of things, then the background around which you expand better satisfies some sort of extremality things. Because after, whatever, because we don't go into more details, but I just wanted to draw this from the conclusion. This is why it would not be unnatural to expect that this thing actually coincides with this thing. This suggests, not proves really, but it suggests S string equals S tilde, because here I said that this thing by construction, the extrema of this thing are the things that allow you to do the quantum theory. And before we said that the extrema of this thing allow you to do the quantum theory. So by joining these two ends, it doesn't seem unnatural that they actually correspond, and they do. And that's the reason why I call this thing the string low energy effective action, because that's what this thing was, right? This is the low energy approximation of string theory.
So, are you saying that those fields are also massive but not very massive, or
Which ones? No, those are massless.
Massive, right?
Yes. Well, if I would be some sort of string phenomenologist, then I guess that there's additional procedures how you, because the hope is that these things, or their analogs, if you do other flavors of string theory, you should be kind of able to beat out the standard model of particle physics out of those. And standard model of particle physics does have masses, right? Like particles around famously have masses. So there is some additional mechanisms that you can use to kind of build some standard model, but you only involve these things. You never talk about these things in phenomenology. So this very massive means like Planck mass. So very heavy. It's like, what is it? It's like Planck mass is like a, I don't remember how much it is. Okay, but a lot. It's like a mosquito per
So
particle.
the massless in this context is kind of different thing than in the context of.
Sorry?
So the massless means like a different thing here, as it does in the context of like a quantum field. Here.
No, it doesn't in the same. No, it's in the same context. It's just that there is further things that you. Okay, I guess you can say that. Like these fields are massless. They are really massless. The way they appear in this supergravitation, they don't have any masses. I guess the way to use them to build massive particles is that you look at you expand them in some strange background, right? Or do some H mechanisms or something. Okay, but let's not get into that because I, in particular, of course, don't remember. But it's not important for us. So, okay, this is the end of the report. Okay, and the fact that these are equal, this can be checked, like explicitly, by calculating scattering amplitudes. And here I'm just using it as sort of like heuristics. That actually, the fact that the critical points of this actually described the condition for the sigma for the thing at the beginning to well defined. Actually, you can sort of think of it as being really the low energy effective action for those kind of fields coming from string theory. Okay. Is there anyone whom I didn't confuse? I was preparing this very carefully yesterday. You know, I wanted to leave some impression and confuse everyone.
You impress us.
Sorry?
You want to impress us.
Yeah, exactly. But was this meaningful for people who actually know the stuff? Ah, okay. Oh, okay. I hope so. This is what I tend to picture behind this. But in particular, I wanted to address this kind of usual dichotomy or whatever. That's like you talk about strings, but then you talk about suddenly there is a metric, a B field, and there are some supergravity actions, and suddenly there is no strings. You know, so what is that about? And well, yeah, it's just how it is. You use different description and accessing different parts of string theory. The thing to remember from this is that there is a metric and there is a B field. That's the takeaway message. And maybe there is a dilophony. And maybe there was some action and there is the reason.
I have a curiosity. So, what is the meaning of a solution of the Ricci flow equation for, like, from a mathematical point of view? Then,
well, what do you mean? And what would be the meaning for like vanishing of the Ricci?
why is it important to solve it as a mathematical point of view?
Ah, okay, okay. Good. Okay, very good question.
My next question would be: does it mean anything to have a black hole, and look at that from this standpoint of a solution of the Ricci flow equation? Certainly does. It is.
Okay.
But I wanted to know what is the mathematical interpretation of this sense.
I can't answer the black hole part.
Okay.
But the mathematical part of this enhanced Ricci flow, so there's a very nice, not really interpretation, but like a very nice application of it. Like you know that the normal Ricci flow has been used in tackling the quantum array conjecture and the Thurston geometrization thing, essentially by okay, it's been used in a way like you pick. You know, these were some questions about geometry, like whether. Okay, so the way it goes is that you put some sort of, you start with some data, and then you kind of try to apply this thing to smoothen it out, and then you hope that you end up with some sort of particularized geometries, and then you can say something about the original thing. So there is an analogous conjecture for the use of these things, which is in the just to classify two-dimensional. So there is, up to now, as far as I'm aware, there is still an open problem of classification of complex surfaces. So if you do four-dimensional Riemann manifold, which are complex, or two-dimensional complex things, there is this thing called code-error classification. It's very complex. Like it's, yeah. I mean, even if you know what a manifold is, to study the complex structures on that is still pretty complicated. But there is even corners of that where people don't even know the diffeomorphism types of the possible things. Like it's not even known up to like. So there's like, I don't know, part 7, type 7 surfaces, something. And those have the, okay, now I'm drifting away, but we're very good at this is inactive. So the problem with these surfaces that are yet unknown, maybe the other parts are also, I don't know, but there is a particular problem with this kind of particular subset of that. And the problem of those things is that they are not scalar. Hence, they cannot be projective. Like they cannot be algebraic, because anything that is algebraic, that you can describe it as the locus of some polynomial stuff, and you can use algebraic geometry to tackle it. It means that it lives in projective space, and since projective space is scalar, it needs to be scalar as well. But those things you know they are not scalar, those surfaces, because I don't know, the cohomologies just don't match. So you need to go outside of the scalar geometry, and that's what this kind of setup with these metric connections with Tor will do for you. Because in general you can have this kind of H field, which is the, normally you should think of it as dB, but actually this can be just any closed free form. So we will in fact be studying pairs like this. So this is a closed free form. And this kind of allows you to go in a direction and apply to problems where you don't, which are not really scalar, but there is like the two form is not closed, but this, you know, d of that two form is this h, and it kind of leads to some, yeah. So you can hope to apply this to study these kind of non-scalar kind of things, which are interesting anyway, and that's what you can use the flow for. It's like a purely math problem in classifying two-dimensional surfaces complex.
Okay. Okay, so this H is interpreted as some sort of smooth torsion. In
Yes.
these cases.
That's
Okay. Okay.
Yeah.
Cool. Nice.
Thank you.
Can I ask, sorry, I forgot to ask you before I like to work, but should I see like some kind of connection between the functional for the area, for the, you know, the number of go to action, and the actual string functional for the fields G, P, and phi?
Yes. So okay. Yeah. So the area of sigma.
Okay.
So okay. Let's start the point differently. So there were two actions. I tried to distinguish them by putting
Yes.
this thing. So maybe there was a phi. Okay, let's ignore phi. I mean, that's what usually we define, and we ignore it. So there is some sort of action for these guys. We don't really know when the sigma is, and there is an action which involves sigma and which treats this uses G. And so G and B are background data that you fix.
But G is not a sigma, right? Or is it?
No, G is not. No, G and B are all the manifolds. Yes. So this thing describes manifolds, metrics, and two forms, and it describes them as a variational problem. So it gives you some, critical point of these are some complicated PDEs which tell you something about this and this. They never talk about any sigmas. There is no sigmas in there. Now the point is that you should see the critical point of this. That those are the right inputs which you can use in this thing.
Yes.
So in principle, as far as the classical variational problem goes, here any G and any B are fine. But if you want to quantize this thing, then you can only quantize it if those data actually is critical point of this thing.
So the tilde one is like the quantization conditions for the first one, right?
Yes. So yeah, the critical point of this is and the gradient of this is really the RG flow, realization group flow for this thing.
Okay.
Actually, okay, there was a slight lie that I said before, maybe correct. So if I said that there is the data need to be critical points of this flow. So strictly speaking, this goes on, so there is like some higher corrections. So the problem is actually much more complicated, but there is some sort of parameter that you usually do your expansion when you work with string theory, and in the lowest order is this thing. But there is corrections. But okay, whatever. This thing is called one loop part of the RG flow. Whatever it is. This is just, to say the usual words, the stuff is much more complicated than you think. Okay, good. So now what we will do, okay, good. So now back to the more firm ground. So what is the plan? So we will see in particular, what we will do is that we will replace in here, in that triple, you replace this thing by a Courant, right? And we will replace metric and B fields together by a generalized metric. We will replace this scalar function by, again, some sort of scalar function, but we will call it. This thing will bring in some interesting geometry that I'm not sure. Just it's how dense it is. It is a different line bundle over the manifold. I will call this G, I will call this sigma. This is my favorite name for this thing. And it turns out that Ricci for G and B and actually much more, but the first approximation of this one, this thing will become a natural Ricci for this data, for G and for G. So you can really unify these things, and this kind of S tilde, which if you remember it was a relatively complex expression, okay, it had 3 terms, but you know, could be easier. So this thing will just turn out to be a very simple object where you have just an analog of a scalar curvature constructed for generalized metric multiplied by this half density squared, and this thing expanded in terms of these fields, it will recover the whole action we have there. Actually, this is true even in a much more general and interesting contexts, but for now, let me say this, that you will recover that from some sort of much more minimal looking part. Okay. Did I persuade anyone that this is interesting?
By naming the things.
Yes, yes. Right? That's beautiful. Okay. Well, then, okay, let's start by recollections. Of the most important thing in the last semester. And I think actually it's probably the only thing that we will need to cover these 10 minutes. So that next time we can start with generalized metrics. But anyway, any questions for this? I mean, this must have been a bit of a, I don't know, vague, potentially.
Woke.
Okay. So, okay, so let's recall our central object of interest. Courant algebra. So, by the way, one thing I should mention is that in last semester we took some time to define this object properly, and then we instead went to supergeometry, and we showed that this thing is much more minimalistic and kind of more natural in the supergeometry context. So now we will actually revert back to the vector bound language for most of the course. And the reason for that is that this generalized Riemannian geometry is actually not yet properly understood in the gradient context. So this is, you can call this like cutting edge questions.
So the sigma squared is like a volume.
Yes, yes. It's better, it's density, but yeah, it's a volume, like a volume form, yeah. It's like, volume form without the absolute value. Sorry, what the volume form with absolute value? This thing exists even on non-orientable manifold. We will get there. Actually, that's the next part of the recollections. So, but let's remember what this thing was. Vector bundle. Working here in smooth category, real numbers everywhere, smooth sections. Okay, so we have some following structure. We have a bracket on the space of sections. Bilinear of real numbers, not over sections. There is a fiber-wise inner product. And there is a vector bundle map, which we call the anchor. Vector bundle map over the identity, just fancy way of saying that at every fiber I have at every point on M I have a map from the fiber to the tangent space. This was called the anchor. Such that, and then there are a bunch of axioms, so the Jacobi identity, not to be confused with Jacobi identity, which is the same, but spelled differently, pronounced differently. Jacobi. So if you remember, these things just tell you the meaning of most of these axioms that I'm writing now is just to say that the structure preserves, all these kind of structures are compatible with each other. The first one says that the bracket preserves itself, so bracket is a derivation of itself. Second one says that the bracket is a derivation of, or the bracket is compatible with multiplication of sections by functions. So f here is a function. So it acts in a Leibniz way. If you have a product of two things, either as product of two sections or product of section and a function. The next axiom tells you that the inner product is invariant. Which, if you think about it, is simply the claim that this is true. And the only axiom that is slightly weird and doesn't fit into this is the one which tells you that the bracket is actually not expected to be anti-symmetric. But instead the symmetric part is something very specific, where this D operator is the composition of D with rho star. Okay, so we start with a function. This is the function on the base. You apply D on it, you get one form. Then you apply the transpose of the anchor, which goes from rho star to E star. And then you identify this with E, which you will do throughout. This uses a pair. Okay, so that's the definition. It's not for the faint-hearted. But then there are some nice consequences which we derived last term. One of them says that actually there is further compatibility conditions that you can expect, but you don't need to impose them because they follow automatically. One of them is that the anchor map preserves the brackets, so it interpoles the bracket on here and here. And yet another condition, or another consequence of the axioms was that if you compose rho star with rho, again I'm using the identification here, and this is 0. In other words, we have a cochain complex. And this leads to the following notion. So we say that a Courant algebroid is exact. If this is exact. If this sequence is an exact sequence, short exact sequence. And in more general, we call it transitive. If it's exact in the last bit, transitive. If rho is surjective. And then there is only one further piece that we will need, and that's to actually give you an example of that. And the classification result, and then I can do it in the 4 minutes remaining. You're supposed to end at half, right? Yes. Okay. We did start like 3 minutes later, so is anyone in a hurry? Is it okay if I take 2 or 3 more minutes? Okay. Sorry for that. But of course we will finish it. Okay, so 2 examples to have in mind. Example 1 is fix closed state form. And then we said, so we take our Courant algebra to be Tm plus T star, so this is the most important one. And for bracket and anchor, you do the only things that you can. Anchor is the projection. And the bracket takes the form derivative. Then there is a term okay, this is example 1. And there is a theorem which says that every exact Courant algebra is of this form, or some H. And in fact, it says more. It says that actually, if you have two H's which are cohomologous, then the two Courant algebras are isomorphic. So in fact, isomorphism classes were classified by the third cohomology. Classified by H3 around. Okay, so this is the first part. This is the most interesting one for us. There is one which is slightly less interesting, but it's richer, so you know. And then the transitive case, example 2. Oh, I can even make it. No. Okay, so this poses the local classification result. Here, this will be local classification result. Because it would be too much to describe the local one. Note that locally, if I would do local result here as well, then I could just set this to be 0, because locally every closed tree form is actually exact. So I can replace this algebra by the corresponding isomorphic one. So I can, if I would formulate local result on the left hand side, then I could hide this H and I could just take off this bit. Okay. So now in this case, choose let G be a Lie algebra with invariant pairing. Okay, so let's do it like this. And then we set E to be Tm plus T star M plus a trivial bundle. Okay, some particular sections of E now consist of triples of vector fields plus one forms plus G-valued functions. There is S and T for these two things, and this will be the upgrade of the thing before. Where I simply add the inner product there. Anchor similarly will be projection and the bracket. The most interesting part is given by, vector part is given by this. One form part is given by this as before, but then there is plus d of s and t. Okay, so s and t are functions which are valued in some linear space, so I can just take a their own differential and make this into a one form valued in g, and then I put the g part here. So yeah, there's only one way to interpret that expression. And then there is a one part which is the, let's say, this is a vector field, this is a function valued in some linear space, so I can just act on that. X on t minus y on s, and finally plus the bracket. Before this week, I really don't remember that we discussed this, or even maybe a more global example in the previous semester. I don't know whether you remember this.
You at least this.
I just
you
didn't
didn't
yeah, you
prove
didn't
it.
prove it.
Right?
No, of course not. Yeah. Right. Okay, so now the corresponding theorem, again, I would attribute it to Cole, is that every transitive Courant algebra is locally, local coordinate of this form for some G. Okay, so those are the two examples, probably the only two examples we will actually need. So there is one on which we have a good handle globally. It's given by third cohomology, classified by third cohomology. And there is another one for which at least we have a good local handle. And we know that locally this is given on a given. I mean, okay, I meant the classic every transplant network over M. Every transplant over M. For a given M is given by simply choosing the Lie algebra of the invariant pairing. Something we call the quadratic Lie algebra. This is quadratic. I think we call it quadratic Lie algebra. Okay. This thing we will use this thing to recover the B field, the metric in B field next time, in some sort of easy way. It turns out it's the same thing here. If you define generalized metric for any current algebra, and then you see what it gives you here. Here it gives you metric in a B field. Here it gives you metric B field and a connection, which is linked to a yet more complex geometric setup where you suddenly have some gauge field and connection, and that one is related to heterotic or type 1 string theory. And this one is kind of more rich, but this one is kind of easier to describe anyway.
Is there a global version of that?
Yeah, there is a global version, which maybe we did. Like you can do more general stuff when you take just as I did here. Here in the global version, I fixed H in this. Here you can fix a principal G bundle. P over M with a connection with A, and on top of that, with a connection, and on top of that, you can fix a tree form, and they need to be named by what's called the Riemannian cancellation equation. So we want that the pairing of the curvature is a 4 form coming out of that. It needs to be DH. So in particular, if you know what it means that the first one pairing class of this bundle has to vanish. Whatever. This is kind of the more general setup. But if in this case you can do 3 forms. Here you can do 3 forms which are not closed, but they're linked with some principal bundle. Unfortunately, it turns out this is not. There is more stuff in the transitive case than just these ones.
So it doesn't specify. I mean,
No, it doesn't. It doesn't. But it does it in like to some like almost. There is a slightly bit. The reason is that when you try to build the global model by patching local models together, and you study the automorphisms of the object in question. If you go on through the Czech cohomology kind of business, and the automorphisms of these things have a little bit more freedom than when you patch principal bundles in some way. Because here, okay, maybe this is. Hopefully, I'm not messing words around, but I think here you can do part of the automorphism of this structure for a fixed G is that you can have automorphisms of G, maybe outer or automorphisms or whatever that you can use to patch these things up, and you don't have those when you build up principal G bundles. Maybe I forgot something like this. So there's a bit more freedom. So actually, the transitive case in general is more richer than this, but in particular, it includes these ones. These ones are called heterotic Courant algebraics, the ones that come from there. Okay, thank you.
Sorry, is the
Yes.
Is the H there uniquely fixed by that?
No.
Like it's Simons 3, 4.
Yeah, it's not uniquely fixed by. Yeah, there is some sort of. How does this work? Yeah, I mean the Chern-Simons 3 form enters into the class. Okay. Okay, I mean here this was like it's determined by these up to some automorphisms, up to some exact 3 forms. In that case, I would have to remember what this was classified up to, but I can tell you next time.
It's some sort of independent piece of data.
Yes, you should think of it as instead of H, I have H and a connection, like more data, or H and a curvature, or maybe one.
Yeah.